And hello, everyone. My name is Paul Wang, and my project is on material selection for bios-inspired self-anchoring microneedles. My advisor is Dr. Hoan Lee from the Rutgers ME departments. The way this presentation is going to break down, I'll start with an introduction to microneedles, a bit about why we're interested in them and what they are. Then I'll go into the background of the work done so far in this project, the current microneedle implementations of our fabricated array, and the way we go about selecting materials for it. Then I'll go into the results section, the way we classify materials for fabrication, radar charts to be created from categories we determined, and some additional considerations that we put in for fabrication. Lastly, I'll go into some future work and conclusions we learned. So to begin, to give a brief introduction, microneedles are miniaturized needles with length scales of hundreds of micrometers. The benefits of this are that they provide a less painful alternative to traditional hypodermic needles, and they are minimally invasive and safer. The advantages of microneedles are that they are more efficient and easier to use compared to traditional needles. The disadvantage is that they typically have low attachment force and are difficult to manufacture because of the needle size. They hold potential applications in various treatments for wounds, skin cancers, slow vaccine release, and diseases like Alzheimer's and Parkinson's. So microneedles are not a new technology, but they do have issues which prevent their widespread use. As I mentioned before, current microneedle technologies are difficult to manufacture, which means that most microneedles are limited to simple geometries like cones and simple pyramidal shapes. And this is an issue because these shapes don't give great adhesion to tissue, so they can't stay in the skin long enough for long-term drug release. Our lab's approach is to develop microneedles capable of self-anchoring themselves into tissue through barbs. Nature has a number of unique methods for anchoring barbs and needles, like porcupine spines, bee stingers, and so we take inspiration from it for our design and use something called 4D printing to construct our microneedle arrays with barbs. 4D printing is essentially 3D printing with a programmed shape deformation that's dependent on time. In this case, time is our fourth dimension. This project is a continuation of work done by Professor Lee's group. So currently they've done work on fabricating microneedles and mechanical testing. The produced microneedle array was able to achieve more than 18 times the adhesion strength of barbless microneedle arrays, compared to microneedles found in nature and previously reported bio-inspired microneedles. The barb version showed at least 2 times and 2.5 times the adhesion found in these microneedles, respectively. However, the fabricated microneedle array has limited practical uses because of its limited coverage area and material limitation. Currently, the size of the microneedle array is restricted to millimeter scales. As you can see in the image, our array only contains around 4 needles in a 2 by 2 millimeter area. This is because our printer's projection area is only 24.4 by 13.8 millimeters, which limits how large an array we can create. This is good enough for basic drug release tests, as you can see in the bottom right 2 images, but it's not sufficient for real-life use when you need a lot of needles to effectively distribute the drug. The material we use to 3D print this array is a polymer called PEGA250. This isn't biodegradable, so to simulate drug release, we let our array sit in a pool of vitamin B. This is essentially a tracer dye for 15 hours before sticking the array into a chicken breast to simulate an insertion. Our polymer material relies on diffusion to release the vitamin B. It's still effective, but if we want more control over the drug release, we need to look into other materials. Additionally, pulling out the array is an issue because the barbs are still present. As I mentioned before, our microneedle has 18 times the adhesion strength of a barbless microneedle, which means it's 18 times harder to remove. Because of that, we need our needles to dissolve or degrade while inside the skin, so that once the drug release is complete, we can remove it easily. Our 3D printing system also has its own requirements. The system requires photopolymerizable thermoset polymer solutions as a material to print microneedle arrays, which prevents the use of biocompatible, biodegradable, bioresorbable materials. So until these issues are addressed, our microneedles are not really useful for practical applications. My work for JG Slade focuses on 2 aspects. First one is expanding the material selection used to fabricate our microneedles, and second is improving the number of microneedles we're able to produce. So to accomplish this, I've been conducting a literature survey on potential materials that would be good for fabricating our microneedles. that also meets our bioresorbable, biocompatible, biodegradable requirements. Again, these are important because once the microneedles are inserted into the skin, they need to degrade and dissolve to administer the drug. The other part of the project is looking into ways to improve the manufacturing process for the microneedles, because our current process is too time-consuming and unscalable. There's two ways to accomplish this. First way involves 3D printing arrays directly, and then stitching the arrays together to scale up the size. The way we do this is print arrays in different sub-areas, and then move our projection in a way so that printing the next array cures it and connects it to the previous one. You're essentially building bigger arrays from smaller ones, stitching them together, hence the term. This way is the most straightforward and simplistic, and it doesn't require us to develop a new fabrication method. Frosseli's group has already successfully scaled up the 2x2 microneedle array to a 6x6 using PEG-250 as a material. I believe you can see that in the left corner, as you can see in image A. However, in order to use this method, our material needs to be directly 3D printable in our system, in addition to meeting our previous requirements. The other way is through replica molding using elastomers. Here we cast a mold of our needles in a curable elastomer to create a mold, which we fill with our selected material and then cure again. You can see the process in the bottom right figure. Afterwards, we pop out the completed microneedle array. This method is a lot trickier, but it has the best potential for fast manufacturing. Our original microneedle model needs to be easily removable from the elastomer molds, and this is a major challenge. We need to ensure that the barbs and the needle stay intact after removal because we want the elastomer mold to be completely empty. That way we can fill it with our new material solution. As I mentioned before, this is extremely difficult. The barbs are backward facing and protrude from needle sides, so a lot of care needs to be taken to ensure they don't break and then get stuck in the molds. Even a structure with simple overhangs, like shown in the figure in bottom right, it's very hard to remove without breakage. We can bypass this issue by selecting a degradable material, which we use to fabricate our original microneedle structure. That's the orange one you see in the bottom right. We use to fabricate our original microneedle structure that gets cast, However, this method means that our final material must come in a curable liquid precursor solution so that we can inject it into the molds. As you can see, these two aspects of the project, researching materials and improving manufacturing, these are intrinsically linked. Selecting a material also determines how we go about the fabrication process and how easy that process is. So we have to be selective in which materials we look at. So after looking through a ton of different papers, I found 7 materials that look promising. These were selected based on their degradation methods and also took into account our lab's fabrication equipment, such as whether we have the equipment to fabricate the material and if we have the knowledge of the process to fabricate it. A variety of degradation triggers is important. The mechanism determines how easy some materials are to degrade and how easy the degradation occurs. For example, a material that degrades under exposure to heat, these are difficult to fabricate because the process is time consuming and it can't be 3D printed as well. But the trigger, which is heat in this case, is extremely easy to use. Materials that rely on enzyme triggers, they can be 3D printed, but their triggers are hard to supply since you both need to acquire the specific enzymes and ensure that it's in constant contact with the material. Some of the degradation triggers I've seen include hydrolysis, exposure to light, enzymes, light solvents, and heat. Figures A through D show some examples of these materials. A is a 3D printable material that dissolves in water. B is a 3D printable material that dissolves when exposed to sodium hydroxide. C is a 3D printable material that dissolves when exposed to an enzyme called chymotrypsin. And then D is a material that dissolves when exposed to sodium bicarbonate. To evaluate which material is best to focus on for fabrication, I evaluated them based on 4 categories. The first one is degradation control. How much control do we have over the degradation process? In other words, how much can we customize the degradation behavior and the time scale? Number 2 is ease of synthesis. How easy is it to make our material? This takes into account our lab's fabrication equipment. 3, 3D printability. This one's pretty straightforward. Can our material be 3D printed? How easy is it to print our structures? And then 4 is material accessibility. How easy is it to get our components for fabrication? This is a little trickier to define. It comes down to aspects like how expensive the components are and which companies stock the components. If it's an international company, accessibility is pretty hard. Afterwards, I rate each category for each material from 1 to 5, 1 being the lowest score, and then I make a radar chart from the ratings to assess their fit. These ratings slightly arbitrary since they're based on comparing the materials to each other. We can't really quantify aspects like 3D printability or ease of synthesis with units. However, since we're just interested in selecting material, this rating system is sufficient enough. The figure at the bottom left is an example of one of the materials examined called GN triethyl. It's a thermal degradable polymer, and as you can see with the chart, it has a 0 in 3D printability, which means it can't be 3D printed. Its other scores are also pretty low, but it's very easy to customize the degradation behavior. The chart on the right is the overall radar chart of all the materials studied, superimposed on top of each other. And next, these are all the radar charts of 6 of the materials. The 7th is in the previous slide. Most of the materials studied are 3D printable directly, and there's a good variety of other characteristic ratings. As I mentioned before, there's also a variety of degradation methods, which influences which material we want to fabricate first. From left to right, degradation triggers are hydrolysis, light, enzyme exposure. Bottom row is chemical solvents, enzyme exposure again, and then chemical solvents again. Most papers I've seen use enzymes or chemical solvents to dissolve their materials, which is reflected in these choices since these two are the most frequent triggers. And with the charts, we can see which materials are best for the project by looking at their enclosed area. The bigger the area, the better. In this case, TAD-T-Bu-PEG, the gel not hydrogel, and the PEG-DA dissolvable scaffolds, these look the best. There's additional considerations we have to take into account though. Using the radar charts isn't the only consideration for fit. I mentioned before that most of these materials are 3D printable, but they utilize a different type of 3D printing from a lab called direct laser writing, or DLW. DLW relies on a different physical process called 2-photon polymerization, or 2PP. In this process, your printing resin absorbs 2 photons at once to induce polymerization. As a result, your printing occurs in a volume called a voxel, and you have extremely high resolution prints, but the process also requires really short wavelength lasers to accomplish. Liquid resin solutions used in 2PP, they're called photoresists. They're meant traditionally for DLW printing. For reference, our printer uses 1 photon polymerization. Instead of 2 photons being absorbed at the same time, only 1 is absorbed. So as a result, our printer relies on a light projection instead of voxel, and it polymerizes cross sections to create a structure. To my knowledge, adapting a 2PP photoresist to our 1PP printer would require cutting the wavelength of the incident light in half. For example, if a DLW photoresist requires 700 nanometer wavelength light, we can print it on our system using 350 nanometer wavelength light. There's also another consideration of whether we can create resin from the material. Most photoresists are easily adapted, but we need to keep in mind properties like resin viscosity. A resin that's too viscous can't print in our system because the movement of the printing platform is inhibited by the viscosity of the liquid, so we can't do accurate prints. The last consideration we need to keep in mind is fabrication knowledge. Whoops, oh, sorry. Fabrication knowledge. Certain materials have processes that are extremely complicated and require specialized knowledge to perform. So we can learn a process to fabricate a material, but the process is time consuming, and we could probably save time by choosing another material that's easier to fabricate. So based on the material study and our selection process, I determined the best materials for fabrication would be the PEG-DA dissolvable scaffolds, the TAD-T-Bu-PEG, and the gel not hydrogel. The next steps for the project would be fabrication. The materials selected will be used to fabricate the microneedle arrays and evaluate their mechanical performance and quality, and we compare the results to our previous tests. After that, we can characterize the drug loading and release kinetics of the new material microneedle array. This is a lot of backtracking on what Professor Lee has done before with a different material. So Professor Lee and his group have done tests already in the previous work with PEG-DA 250, which is the current material we use for our arrays. So this test just needs to be repeated for new materials. The drug release test is shown in the bottom right chart. Of course, with the results of this material selection process, we can push our microneedles closer to practical use and possibly commercialization. Using material from this list ensures that we're able to meet our biocompatibility requirements, while also opening the door to mass production of our microneedles. So I believe this concludes my presentation, and thank you all for listening.